This video will present many of the engineering details that went into fabricating a high-power Excimer laser. A number of things will be presented which may seem a little strange to the average engineer or technician. For example, this device. Is it a high-voltage switch? Is it a diode? Is it a saturable inductor? The fact is, it's a saturable inductor, and it can behave as a high-voltage switch or a diode under the right conditions. Most people familiar with electronics will recognize the top two items in this view as inductors. However, the bottom two are also inductors. The one on the left is called a strip line inductor, and the right one is a coaxial inductor. I will also be describing a device called an LC Inversion Generator. This is something that not a lot of people have run across, but it is a very clever way for producing high voltage, high current pulses. Then I will show how all this can be combined to produce a laser. Let's look at the LC Inversion Generator in a bit more detail. Ignore the charging circuit for the moment and concentrate on capacitor C1, C2, inductor L1, and a switch. Notice also that the voltage out is approximately 0 initially. When the switch closes, current will begin to flow from capacitor C1 through inductor L1, and this will reverse the voltage on capacitor C1. When the capacitor C1 is inverted, this produces an output voltage of approximately twice the input voltage, although opposite polarity. You may have noticed when capacitor C1 inverts its polarity, diode D2 would begin conducting and drain that charge through power supply V1. Let's take a look at the actual charging circuit and see how this is prevented. Before going into further details on the LC Inversion Generator, let's look at the circuit that is used to charge those capacitors to 30,000 volts. The charging circuit consists of a capacitor C-store, a thyratron switch, and a constant current power supply of 30,000 volts at 1/2 amp to charge the capacitor. The thyratron switch behaves very much like a thyristor or SCR, more familiar to most engineers. When the thyratron switch is triggered, current begins to flow through L charge, and this charges up the 0.22 microfarad capacitor shown on the right, which is actually the two capacitors C1 and C2 in the inversion generator. This shows the voltage and current waveforms in the thyratron circuit. When the thyratron is triggered, the current rises to a peak value of approximately 5,000 amps and returns to 0, whereupon the current stops flowing, as it would in a thyristor circuit. This is what prevents discharging the capacitor C1 in the inversion generator. Notice also that the voltage on the inversion generator goes from 0 to approximately minus 30,000 volts in the 2 microsecond time period. Now that our LC Inversion Generator is fully charged, let's close the switch and look at the current in L1. Suppose that we can arrange for the switch to close just at the time when the thyratron has fully charged the capacitors, about 2.1 microseconds after we triggered it. Note that the current was slowly increasing from 0 to approximately 70 amps during the 2.1 microseconds after the thyratron was triggered. At this point, the switch current suddenly increases from 70 amps to approximately 70,000 amps, and this is the current that inverts capacitor C1. The 70 amps of current is due to leakage in the switch, which I will explain a little later. Now that our LC Inversion Generator is fully inverted, we're ready to add on the laser load. The charging circuit is no longer relevant. Since switch SW is open, L1 also is no longer relevant, and since the output voltage is reversed, diode D1 is no longer relevant, so they will be removed from the circuit. The inductance is the parasitic inductance of the connections between the LC Inversion Generator and the laser electrodes. The switch is not a real switch. It simply represents the point where the voltage becomes high enough to ionize the gas, causing a large amount of current to flow through it. The resistor represents the voltage drop of the ionized gas divided by the current flowing through it. When the gas is ionized and current starts flowing, the load current goes to a peak of about 80,000 amps, and voltage across the gas collapses during this time. The power seen by the gas is on the order of 2 to 3 gigawatts over a time duration of about 50 nanoseconds. This extremely high power and short duration is exactly what is needed for the gas to absorb energy, since Excimer gases tend to collapse into an arc after about 40 to 50 nanoseconds. The inductance can be calculated from the inductance of a strip transmission line, since the parallel metal plates closely resemble that type of object. Strip-line inductors can be useful for connecting two parts of the circuit together. However, they frequently appear as a byproduct of something else. For example, a capacitor bank might consist of several capacitors bolted between two copper plates. These copper plates have inductance, and it must be included in the calculations for the circuit. Coaxial inductors can also be useful in certain circumstances. For example, in our laser system, our coaxial inductors consisted of a piece of 3-inch diameter copper pipe with an inner copper pipe of about 1.5 inches diameter, and these are connected to a common metal plate at the end to produce a single turn shorted inductor. We fill the inside of the air core inductor with ferrite toroids, which makes it an iron core inductor. The ferrite cores used were manufactured by Ferrox Cube. They were a 74 by 39 millimeter core, approximately 13 millimeters thick. It required approximately 48 cores to fill the inductor. The ferrite material of choice was 3E6, which has a relative permeability of approximately 10,000. This gave us an iron core value of approximately 850 microhenries for each inductor. To understand a little bit about magnetic saturation, we need to look at BH curve of the ferrite. This is a typical BH curve. It shows magnetic flux density B in Teslas plotted as a function of magnetic field H, which is measured in amperes per meter. The relative permeability of the material is determined by the slope of the BH curve. For low magnetic fields, the slope is very steep, yielding a high permeability. Once the magnetic material reaches saturation, however, the flux density becomes very flat, and as a result, the relative permeability approaches the air core value. This is the basis for our using a saturable inductor as a switch. When the switch is off, it has high inductive reactance, that is, the inductance is high. When the switch is on, it has low inductive reactance, that is, the iron is saturated. We start with the inductor in low magnetic field, part of the BH curve. A voltage pulse is applied across the inductor. This causes the current to increase slowly until the magnetic core saturates. Then it will rise rapidly when the inductance decreases due to saturation. The core must be reset to get to the starting point before the next pulse. That was a lot of information in a very short period of time, so let's stop and examine some of the details of this a bit more. We already looked at how a saturable inductor can have either a high inductive reactance or a low inductive reactance by either being in the unsaturated state or the saturated state. First, let's examine how the current increases slowly until the magnetic core saturates and then rises rapidly when the inductance decreases. For starters, we can look at the voltage across an inductor, and the voltage is the inductance L times the dIdt, where dIdt is a rate of change of current with respect to time. A rate of change of current with respect to time is nothing more than the slope of the current. And I'm going to perform a little bit of calculus on this, but don't worry, I won't overwhelm you. First, we rearrange the equation, getting di on one side of the equation and all the other variables on the other side. Then we take the integral of both sides of the equation. The integral of di is simply I, and the integral of v dt divided by L is the voltage times time divided by the inductance. Since both the voltage and inductance are a constant until the iron core saturates, this means that the current is going to gradually increase with time until it reaches the point of saturation. Once saturation is reached, we use the same equation. However, now the inductance is a much smaller value, which means the current will increase at a much faster rate. The 70 amp value is not a hard and fast value. It just happened to be where our switch saturated, given the bulk of ferrite that we had and the length of the magnetic core and the voltage that was applied to it. In fact, if the current does reverse, it could well go to any value along the curve, so the magnetic flux density would be an unknown value. To overcome this and produce reliable, consistent switching, we use a reset. Magnetic reset is achieved by passing a DC current through the core to set the value at a point along the BH curve where we wish to start. The starting point on the BH curve can be either positive or negative, depending on the polarity of the supply we use to provide the current through the iron core. Note that the single turn of high voltage wire through the transformer core produces a pulse transformer, which would be transmitting approximately 40 kilovolt pulses back into your power supply unless you put in the blocking inductors L10 and L11. Since this particular saturable inductor saturates at around 70 amps, it is necessary to have at least 70 amps of bias current available from the bias supply to achieve the desired result. Also, the inductors L10 and L11 must be air core inductors so they do not saturate. An added advantage of reset relates to operating the laser at higher or lower voltages. The adjustable bias supply can be used to set the reset point along the BH curve such that it reaches saturation at the 2.1 microseconds for voltages lower than the 30 kilovolts. Now let's look at the saturable reactor as a diode. Since a diode conducts current more readily in one direction than another, it tends to have a high voltage drop for current in one direction and a low voltage drop for current in the opposite direction. We can achieve the same thing with our saturable reactor by biasing it near the point of saturation, so any further current in the same direction will cause it to go further into saturation, producing a low inductance, and any reversal of current will cause it to go into a high inductance state. This effect is used to advantage here to hold the voltage across the laser electrodes at a low value while the capacitors are charging. Then when the voltage reverses, it provides a high impedance so that very little current is diverted away from the discharge. Now let's see how all this mechanical assembly goes together to make a laser. The LC Inversion Generator is attached to two saturable inductors, both labeled L1 here, since there are really two circuits in parallel to reduce the inductance. The saturable inductor D1 is placed from the output to ground to provide a low impedance during charging and a high impedance during electrical discharge of the gas. A set of laser electrodes are attached to the device along with ground returns. Note that the ground returns have a small cross section in one axis to allow for gas flow between the electrodes to allow a fan to sweep out the used gas and replace it with fresh gas between pulses. This whole assembly is placed inside an insulating tube that is filled with oil for insulation and to help cool the saturable inductors. The tube has end caps attached to it and is placed inside a larger pressure vessel to hold the laser gas, as well as the fan and heat exchanger, which are not shown in this video. Metal end caps are attached to the laser vessel, along with windows for light to come out, and an opening for the wires connecting the thyratron and charging circuit to the LC Inversion Generator. The thyratron is placed inside a metal container on the end of the laser with the storage capacitor located just behind it. High-pressure gas lasers such as T lasers and Excimer lasers require some form of pre-ionization to start the conduction process. One form of pre-ionization is called corona pre-ionization, and it's usually accomplished by placing an insulating tube such as a quartz tube near the metal electrode and connecting a wire inside it to the opposite electrode. As high voltage is placed between the electrodes, the gas surrounding the quartz tube will become heavily ionized and produce a large amount of ultraviolet light, which tends to ionize the gas in the volume between the electrodes. One method of accomplishing this is to bend the quartz tube in an arc so that it has a long path along the surface to prevent arcing along that surface, yet still provide the pre-ionization and a means to connect the wire to the opposite electrode. In this laser, an array of 4 quartz tubes is used, extending the full length of both electrodes on each side to provide copious amounts of ultraviolet to pre-ionize the entire volume. The result is a nice uniform glow discharge between the electrodes during the high voltage pulse. I hope you found this video informative and perhaps entertaining, and I also hope that maybe you learned something that you didn't know before. If you have any questions, please list them below. Thank you for watching.